Alright, so here in the second video, we're in 3 dimensions, and the story is very similar. That once we've written down what it means to do a triple integral, which, by a very similar result to the two-dimensional case, can be done almost always by considering just the iterated integrals in each variable independently, and has this similar results about being able to exchange the orders of integration. Our change of variables formula, it looks essentially exactly the same, except for the fact that, of course, to describe a three-dimensional region, we need three new parameters, so u, v, and w, and that means that our determinant, the absolute value of the determinant of the derivative of that change of variables function is going to be slightly more difficult to compute. And there's, of course, a small typo here in that this should be a triple integral across the region d star. All right, so in practice, we've got quite similar tasks. So here, we're interested in computing the volume of some certain region, this parallel piped, the sort of dimension up generalization of a parallelogram. Here it's defined in terms of 4 points: the origin 1, 2, 3, 1, 1, 1, and 0, 4, 2. And so I will not attempt to draw it in sort of standard orientation where we're looking in, down at the positive quadrant. But we've got some shape where, let's see, that's that line. There's in the back another one, and we know what, I suppose I should probably have picked a different corner to be the origin, but we know what three of the legs of it are, and so we know that the other boundary points would be given as, since we're starting it, we've already translated a corner to the origin, the other boundary points are going to be given by sums of either two of the other two coordinates for that point, and that point, or the sum of all three of the coordinates for that point. So we could write down what all the boundary points are, but we'll see that ultimately just knowing which edges intersect the origin is going to be enough, that if those were along the axes, you would have length, width, and height. And so our difficulty here is that this parallel pipe that we've been given is not aligned along the axes. It doesn't wind up being sort of simple to integrate along any direction, and I suppose we could just attempt to figure out from linear algebra what these lengths are, but I want to talk about doing it with an integral because it's a good example. And so what we would want from a change of coordinates that would make this reasonable is we would want to consider a change of coordinates for which our resulting region is a rectangular prism is aligned along the axes. And so to do that, we would say, we want each sort of leg here of each side to be governed by only one of our new variables, u, v, or w. So we could say that this is the leg given by u, this is by v, and this is by w. And if we can figure out what, then our bounds are just going to be like from 0, because we're starting at the origin, and we might as well translate the origin to the origin. Then our bounds are just going to be, we want, we could even say that we can account for speed in the function f that we're constructing, and say that the bounds in u are just going to be from 0 to 1, and u equals 1 is going to give us this point. And because if we use a linear transformation, it'll take lines to lines, and our parallel boundary points are all going to move along. And so what we want is for essentially u to be contributing factors of, I didn't write this very well, of this first point. We want v to be taking us towards the second point, and we want w to be taking us towards this third point. And so to accomplish that, we could say that if x, the x coordinate that we're at in our parallel pipehead is we've contributed, we might have some from having traveled in the direction towards this first point, which is parameterized by u, and we might have some that are gotten by traveling towards the second point, which is parameterized by v, or motion towards it. And motion towards the last point, isn't going to change it. Similarly, y, we could have gotten some from going towards this first point, and it's coming in like twice as much if we go halfway to the first point and say u is a half. Then we would have gotten a full value of y. We get 1 for every unit towards the second point we get, and we get 4 for every unit towards the third point. And z is going to be 3 for as much as you go to the first point, 1 for as much as you go to the second point, and 2 for as much as you go to the third. And so if we plug these in, and we say that d star is just going to be the unit cube, as like our parameters, then our question is just, what is the appropriate volume element, and then what is the integral of that volume element. And then we might also be interested in this integral of x times that, which I'll talk about why that's a thing to naturally care about in a second. But first, that if we think about the absolute value of the determinant of our change of variables matrix, we're taking the absolute value of the determinant of first row is going to be partials of x, and so partial x with the u and with the v is both 1. We get a 0. We get 2 u's, 1 v, and 4 w's as the derivative for y, and 3, 1, 2 for z. And so we can see that this matrix actually has columns, these 3 points, which is what we kind of constructed it to be, that the first coordinate is contributing factors of 1, 2, 3, that the second is contributing factors of 1, 1, 1, and the third of 0, 4, 2. And so if we compute this determinant, we've got an overall absolute value. If we do cofactor expansion along the first row, because we've got a 0 in it, we get a 1, 4, 1, 2 minus the determinant of 2, 4, 3, 2. If we look at these, we get 2 minus 4 minus 4 minus negative 12. And so those come out to be overall 6, constant 6 as our scale factor. And so our triple integral over the parallelepiped P that we were interested in, just a volume, is going to be an integral from 0 to 1 in all of our variables of 6 du dv dw. And because these are all integrals of constants, we're just going to get 6 overall. That integrating du, we just get 6u, evaluate at 1 is 6, and then do the same for v and the same for w. Very similarly, if we were to write down the integral of x dv, we again get 0, 1, 0, 1, 0, 1. Here we have to write x in terms of u, v, and w, but we've already done that above. We get u plus v. And then let me move that down a little bit. So we have space. When we do the u integral, we're going to get a half u squared plus uv evaluated at 0 and 1. And so 1/2 of 1 squared plus 1 times v is going to be our new integral. Again, that's 0 and 1, and there was a factor of 6. Which I forgot to write up here as well. The factor of 6, which is again the same, is this one that was coming from our change of coordinates, the determinant of that Jacobian. And then here, the 1/2 v plus 1/2 v squared is going to be our antiderivative. Evaluating that at 1, we get both of them equal a half, and so we get just a 1 as the second integral there, and then we're integrating, we've got 6 times the integral from 0 to 1 of 1 dw, which is just going to give us 6 again. And so here I want to mention why I included that, is that if we were to then also compute the triple integrals of y and of z respectively, we could use that to find the average value over this volume of x and y and z by just dividing our values by the volume. And so here we've shown that the average value of x is 1, and that kind of makes sense because 2 of our sides here have x coordinate 1, and the last one doesn't involve x, and so these two are going to be sort of midpoint sides. And the last corner is going to be with x value 2. So if we did that for y and for z as well, we'd be able to compute the sort of center of mass of this object, which is like a way that these computations show up in physics quite often. Physics and sort of related concepts for statistics and whatnot. So it's a very natural computation that we would be interested in doing. Okay, too fast. So similarly to polar coordinates, in 3 dimensions, there's these sort of two very canonical choices of coordinate system, spherical and cylindrical. And they're both generalizations in different ways of polar coordinates. So for spherical coordinates, we're measuring, again, first, the first coordinate is going to be the radius away from the origin. And so here it's a radius, of a sphere away from the origin, and then we need two different angles. And the usual choices is one, measuring the angle in the xy plane that we're lying above, and so that's the angle that only depends on x and y. And then the other angle, phi, here is going to be measured down from the z-axis. And so our point with phi equals 0 is going to be, if we had radius 1, theta, well, any value of theta, and phi 0 would be a point that's lying on the z-axis. It's important to note that while this is a convention we're using, it's also fairly common to have the convention where the last angle in spherical coordinates measures up from the xy plane, and so phi equals 0 would be on the xy plane rather than along the z-axis. If you're using resources from different books or encountering other people talking about this, it's very important to check which convention is used because they're both fairly common. But like I said, the one that we're using here most commonly is going to be measured down away from the z-axis. The volume element here, and this is a good one to sort of just remember, is going to be rho squared sine phi, d rho, d theta, d phi, or different orderings of those. And it's important that phi is this other angle, the one from the z-axis, and not the one in the xy plane. The one in the xy plane doesn't change how the volume scales. The other generalization that's used of polar coordinates is cylindrical coordinates. And so here we're essentially just taking polar coordinates in the xy plane and leaving the z-coordinate on its own. Although, of course, people will sometimes talk about cylindrical coordinates along different axes, but the usual one is with the z-plane, having the last coordinate measuring height, z, and then the first few coordinates is just actually polar coordinates in x and y. So here our volume element would be r dr d theta from the area element of polar coordinates, and then just times dz because we've kept Cartesian height, and so we even just can write this as z equals z. Be a little bit cheesy there. And so these are both changes of coordinates to both remember the formulas for what x, y, and z are and what the volume elements are for them, and they'll often simplify computations that have spherical geometry, or that have polar geometry in one of their planes or something. Last thing we have is this integral of what looks like a spherical radius, x squared plus y squared plus z squared, over a region that's defined more in terms of cylindrical coordinates. X squared plus y squared is equal to something in terms of z, z itself, absolute value z. And so here we've got this tension where we've got to decide, do we prioritize the region and do cylindrical coordinates for our integral, or do we prioritize the integrand and use spherical coordinates, and do more work to talk about what this region is? And so here I think it's going to be almost always the case that the correct move is going to be to prioritize the region, that looking at this x squared plus y squared in terms of z is going to be something that's going to tell us that we need to be setting stuff in terms of cylindrical coordinates, and we'll figure out what's going on with the integrand later. And so here we can see that the sort of good choices here. We don't have any dependence on theta in our bounds of our integral, so if we're trying to set up, or of our region, and so if we're trying to set up the bounds of the integral, we can see that theta is going to explore its full range, 0 to 2 pi. Similarly, we're going to have z is going to be able to range from, we can see between -1 and 1. We'll allow the right-hand side to have non-negative values, and we know it's going to be equaling a square, so that is required for it to make sense, and we've got a correct value for any of them. And so we're going to be able to say that z should range from -1 to 1, and then r is always going to be non-negative, and we know that it goes up to 1 minus the absolute value of c is just given directly. Sorry, the square root of that, because this was r squared. And so here, as we set up this integral, we've got our bounds. Our function here is going to be r squared plus z squared, which is not that bad. And so we can do the integral directly. And here I think I want to do the order with z first, then r, then theta as the innermost one, because it'll turn into a constant as fast as possible. And so we've got z ranging from -1 to 1, r ranging from 0 to the square root of 1 minus absolute value z. And theta from 0 to 2 pi. We've got our function is r squared plus z squared. R d theta dr dz. And here we can do one last simplification, which is observing that our integrand depends on z in a way that doesn't care about the sign of z, that we've got only a z squared. And so if we were to switch to -z, we wouldn't be harmed. And our bounds also aren't different based on the sign of z. That 1 minus the absolute value of z is agreeing with 1 minus the absolute value of -z. And so rather than doing this integral fully in z from -1 to 1, the bit from -1 to 0 is going to be exactly the same as the bit from 0 to 1, both in what we're integrating and what the bounds in r are that we're integrating over. And so we can actually say that this is 2 times the integral from 0 to 1 in z. Of everything else that's going on the inside, where we've got this factor of 2 just to account for the fact that the bottom and the top region look exactly the same. And that'll help us by letting us write the r bound as the square root of 1 minus z if we're considering only the positive part. We could also have gotten very similar results by just splitting up our integral as the integral from -1 to 0, and then the r bound is 1 minus -z, because the absolute value of z when z is negative is of course -z, and then adding that to the integral from 0 to 1 of the square root of 1 minus z itself. But I think it's worthwhile to point out the fact that we can get away with this factor of 2. So multiplying that in and then doing this integral in theta, that our integrand doesn't depend on theta, so it just becomes a constant. We get this overall factor of 4 pi. Our changed bounds in z, and the bounds in r that we can get away with, 1 minus z. And then here I'm going to multiply out what we've got. So we've got an r cubed plus an r z squared dr dz. And then here we've got our polynomial. We can carry over the factor of 4 pi, 0 to 1. R cubed is going to go up to a 1/4 r to the 4th. And r z squared is going to go to 1/2 r squared z squared. Evaluating both of those at 0 gives 0, so we only care about the evaluation that's square root of 1 minus z. And because we're plugging these into even powers, this works out pretty nicely, that we get a 1/4 times 1 minus z squared from the 4th power plus 1/2 1 minus z times z squared from taking the square root of the 2nd power, doing that integral dz. And then this, we can start, we can start multiplying things out, so I will even multiply that 4 into clear out all these fractions. And so we've got pi times 4 over 4 is just going to give it a factor of 1. And this is going to be 1 minus 2z plus z squared. And then plus 2 times everything that goes on here, so 2z squared minus 2z cubed. This last step, these are all polynomial terms, so we can carry out this integral. We've got our factor of pi. We only care about the terms at 1, because they're all polynomial. At 0, they go to 0. And so we can start just keeping track of what we get. 1 integrates to z, so we pick up a factor of 1. 2z goes to z squared, so we get a minus 1. Z squared goes to, or rather, we've got a z squared plus a 2z squared, so we've got a 3z squared here, which goes to z cubed, which is giving us another 1 to the positive. And then this last term, we've got 2z cubed, which is going to go to minus 1/2 z to the 4th. And so all of this is going to give us a final value of pi over 2. Which is the integral that we were looking for from the very beginning. Alright, so that's what I have for today. This was the second and last video, so be sure if you came in the middle to check for the first video, and otherwise I will be back next week.